Hello friends, MoNaCo here, fourth lecture notes on heat. Q equals MC delta T is the equation that we're going to be going to study in this particular lecture. That is the heat calculation question, and that is the foundation of any heat transfer calculation that needs to be done. If you're thinking about how heat affects objects, that equation describes how much heat, as in joules, the object absorbs or releases when it comes in contact with another object that has a different heat. And heat and temperature aren't the same thing, but temperature is part of the heat calculation. So we're going to be using some basic algebra to investigate how much heat changes the temperature of an object, or how much heat is changed when the temperature object changes. So this is the equation that we're going to be using. And the definition of heat is the energy transferred due to a difference in temperature. So if you have a hot object and it comes in contact with a cold object, you know that heat is being transferred from the hot object to the cold object. We're just going to be putting numbers on that. So if you want to envision in your brain what's going on in these type of equations, think about this. You take a cup of cold water and you put it in the microwave and press the heat button for 30 seconds. The temperature changed, obviously, but by how much energy did the microwave put into your water is kind of what we're trying to answer. So Q is a value that we ascribe to heat. It's in units of joules, or J's, okay? If you divide your joules by 1,000, you get to kilojoules, okay? Sometimes you'll have to do that. M is the mass of the sample that we're talking about, and usually we're talking about grams. Got to use grams for your mass. C is a value called heat capacity. Table B in our references calls out the heat capacity of water. Heat capacity, on a grander note, is how much energy it takes to change the temperature of an object by 1 degree. Different materials, since they're made out of different elements, have different heat capacities. We usually focus on just water in this course. Delta T is a change in temperature, and you calculate it by doing temperature final minus temperature initial, or some people do it by temperature initial minus temperature final. Either way, we always like to do the absolute value so that we don't have a plus or minus on our change in temperature. You can do it with a plus or minus, but it makes our calculations a little bit more confusing. So whenever we do these type of heat calculations, we're looking at problems that involve changes in temperature, and it asks how many joules are absorbed or how many grams of a material that we've got. So you identify a heat calculation because it asks how many joules. And we always use this equation, Q equals M times C times delta T, when there's a change in temperature involved. So we're going to define from our problem Q. It's asking how many joules, and Q is therefore X joules. We don't know. M, 50.0 grams. We're talking about water in this case, so we have to look for the C value from table B, and that is, since I've memorized it, 4.18 joules per gram degree Kelvin on our reference tables. And to find the change in temperature, we take our final temperature, 58.6 minus 30.2. Calculate that, 58.6 minus 30.2. And that is 28.4. I'm going to say those are degrees Kelvin because remember, a Kelvin degree and a Celsius degree are the same size. So we can interchange the units easily when we're talking about changes in temperature. So we're going to use that value for our delta T. So now we go back to the original equation and start plugging in what we need to know. Q is X in this case. M is 50.0. C is 4.18. And delta T is 28.4. So in this particular example, we have a straight plug-in chug. And at the end, we're going to get a value with the units of joules for the how much heat, how many joules are absorbed when 50 grams of water are heated from 30 to 58. So that's the value you're going to get there. I want to see that calculation when I check your homework. Different variations of the same equation involve finding out the other variables like C or M or delta T. So we are going to talk about the specific heat of silver and finding it. It's asking what is the specific heat of silver when we have a 93.9 gram sample cooling from that temperature to that temperature with a loss of heat. So again, this is the same equation. Q equals M mass times C, specific heat capacity, times D, delta T, change in heat. Change in temperature, sorry. So we define our variables. Q, in this case, is 428 joules. M, 93.9 grams. C, the specific heat is C. So we're going to look for that. That's X. And the change in temperature, in this case, is 215 minus 196, 19 degrees Kelvin. Or Celsius, they're the same size units, so it doesn't really matter which one you put in there. We use Kelvin because our C value has the units Kelvin in it. So we go ahead and plug into the original equation. 428 equals 93.9 times X times 19. To solve for X in this case, you're isolating X by itself on one side of the equal sign, which means you're going to have to divide by 93.9 times 19 on both sides. 93.9 times 19. That is some basic algebra there. They cancel out on that side, leaving you with X equals a value, and the units will be joules per gram degree Kelvin, because those are the units for specific heat capacity. I want to see you calculate that value. And this it will not be the same as that on table B, because this is talking about silver, not H2O. Next variation on the equation. 100 joules are added to 20 grams of water at 30 degrees. What will the final temperature of water be? So the key terms here, 100 joules, that's heat, added 20 grams, that started at 30 degrees. What will be the final temperature? So we have to find out the final temperature by way of finding out the change in temperature and applying it to the original temperature. Either way, we're still using Q equals M times C times delta T. And we define our terms. Q equals 100.0 joules. M equals 20.0 grams. C, we can figure that out because we're talking about water. Look at table B for the specific heat capacity of water, 4.18 joules per gram degree Kelvin. And delta T, in this case, is X. We don't know it. That's what we're finding out first, then we're applying it to our 30 degrees. So two-step problem here. The first step, 100 equals 20 times 4.18 times X. Isolate X, dividing both sides by 20 times 4.18, algebra, times 4.18. And that will give you X equals the change in temperature, equals delta T, some value. The second step, you take your original 30 degrees Celsius and add delta T to it, because we added the heat in this problem. So their final answer will be something larger than 30 degrees. It's the final temperature of that cup of water after you added 100 joules of heat. Simple enough. Algebra, people, algebra. Last variation here. Temperature of a sample of water, liquid phase, is raised by 30 degrees by the addition of 3762 joules. What is the mass? Okay, so we have Q, heat, mass, specific heat capacity, and change in temperature. So we plug in we define, then we plug and show. Q, 3762 joules. M, what is the mass of the water? We don't know. We don't know how many grams we've got here. C, since we're talking about water, we can use the specific heat capacity of water, 4.18 joules per gram degree Kelvin. And the change in temperature, well, liquid phase, the temperature was raised by 30 degrees Celsius, so we can say the change in temperature is 30 degrees Kelvin, because again, a Kelvin degree and a Celsius degree are the same size. Plug it and chug it to solve for mass. 3762 equals X times 4.18 times 30. To isolate X by itself, you divide both sides by 4.18 times 30. You can do it in whatever order you want, but you have to divide both sides by both of these values. They cancel out on the right-hand side, leaving you with the value x equals some unknown quantity of grams of water. And that's what I want to see for your calculations in your homework. Now, at this point, you should have the basic understanding of that heat calculation and how heat is changing the temperature of an object and how we can quantify that now. You can do some of the pages 4 and 5, some of the problems. After the next video, you'll be able to do all of pages 4 and 5. Thanks for watching.